So today I'm starting lecture 51, and in this lecture we are going to discuss some more topics on response surfaces, typically about the robustness of design, which is one of the key features which comes out by using response surface methods. And again, I am Dr. Ranjan Ganguly, and this is lecture 51 of the optimization series. So we have crossed the half-century mark at this point. So I hope you have benefited from these videos and will continue to do so for the further videos. Now we have seen that response surface methods essentially try to solve a number of issues which occur in practical design optimizations. And these are not discussed frequently by people in nonlinear programming communities, because much of the basic research in this field is interested in finding the minimum of functions and developing methods which are good for particular kind of functions. But in reality, when you are trying to use optimization in the industry setting, which is really the aim of any kind of engineering research, one of the problems which comes up is that all the engineering work or analysis which is done nowadays is using computer models. And essentially, when you run these computer models, you get what is known as a simulation. And essentially, these computer models being very cumbersome and large pieces of code, it's difficult to link these computer models with optimization algorithms. And response surfaces let us decouple these two processes. And again, we have discussed this aspect in detail before. So today we are not going to discuss this aspect. We are going to discuss the aspect of robust design and numerical noise. So now what is a robust design or a robust minimum point? So let us say we have a function f of x. This is a one-dimensional function for simplicity. And I plot this function with respect to design variable x. Now let's say the function profile looks somewhat like this. Now by looking at this function, you would see that at least in the design space we have created here, the minimum point would be A. So from the point of view of the gradient being 0, you would have 2 points where the gradient would be 0. One is this point here A, one is this point here B. You would classify B as a local minimum point, you would classify A as a global minimum point, and you would probably go and take this value A and report it to your supervisor as the particular minimum point. Now, an important fact to realize is that suppose I were to manufacture this particular system for which f of x is the driving objective function or cost function, and somehow the x value which I obtained from manufacturing differed slightly from the value I have suggested to the manufacturer. So you could see very quickly that suppose my point was somewhat off here, you would quickly go to some point here, which would actually be greater than the point B. And therefore, this minimum point is not robust to any small perturbation in the design variable x. And therefore, I can say that A, though being a global minimum, though having a lower value of the function f of x, is actually a less desirable point than this point B. Now this point B is more robust because if I had a slight shift in terms of manufacturing, so uncertainty is present in this variable x, my objective function doesn't degrade too much. And that's an example of a robust design. Now what would a response surface do? If I tried to fit a response surface through data points obtained from this curve, I would obtain some curve fit which would essentially be like this. So the curve fit is likely to smooth out this particular deep local minima, and it's going to make this the main minima in which you get your solution. So this is one of the aspects which happens in response surfaces, and especially happens in the case if you have a lower polynomial, for example a quadratic, to model this kind of a surface. So essentially this is how you get the robust minimum point. So to conclude, point B would be a robust design for this particular function. Now we also see that optimal points are useful in engineering design if they are robust, because if they are robust, then only they are not very sensitive to small perturbations in the design variables as well as the system parameters. Now the system parameter issue comes across because there are also some parameters out there in the ambient atmosphere. For example, you may have parameters such as the temperature, the pressure, the level of heat in the day, the wind speed, and so on. Now some of these may not actually be considered during this kind of optimization process, but still we see in most cases that a robust design obtained using response surfaces would show somewhat better characteristics in terms of robustness to system parameters also. Now again, you can formally address some of these issues in robust design, so we are not going to really look at the concept of RDO and RBDO here, where you actually use not only the objective function, but you also try to minimize the standard deviation corresponding to the cost function for the problem. So again, that is a more rigorous way of doing this problem, but that also becomes computationally very expensive. And this kind of response surface method is much less computationally expensive way to handle this robust design problem. We see that the need for robustness comes because perturbations are often present in the system. For example, whenever you try to manufacture something, there may be some minor deviation from values you have given. You also have uncertainties present in material properties, boundary conditions, geometry of systems. So the properties which are actually used in the simulation, which you are using to get the particular optimal solution, are not the properties you get in the real system. And therefore, not only are you using the response surfaces as a guide, but you are using the model itself as a guide for the real world. It's not exactly the same as the real world. Therefore, all these type of uncertainties which are present in a real system can be addressed to some extent by the smoothing nature of the response surfaces. Now, of course, material properties would involve something as simple as Young's modulus and Poisson ratio. We presume these are deterministic numbers, but in reality they are random variables. We may consider boundary conditions such as a clamped condition, simply supported condition, a free condition for a beam, for example. But in reality, boundary conditions are more complex. They do not exactly model any of these conditions in reality. We may consider different aspects of geometry of systems. And again, these also may be slightly different. For example, if you are looking at the topology of a certain shape, it may slightly deviate from what you have considered in the model. So all these factors essentially deviate the computational model from reality. So the main aspect about response surface is that they smooth out the deep minimum in the problem. And again, keep in mind that this is largely accomplished by fitting polynomials which are typically order low. For example, a quadratic polynomial would be better than a fifth degree polynomial, because the problem which a fifth degree polynomial would have is that it would try to fit in the deep local minima and get that value. So that is something which is smoothed out when you use quadratics, for example. So again, to put this deeply into your mind, if you are using response surfaces, if you are moving sequentially in the design space, you are much more likely to land on to problem B, which is a robust design, through some kind of quadratic fits and get a better solution. Now, one more aspect to consider, which is related to numerical noise, is that most engineering problems rely on computational methods. and these rely on solution of some kind of discrete partial differential equations in the spatial and temporal domain. Also, you have nonlinearity present in many problems. And one of the things which happens when you have a combination of nonlinearity and partial differential equations and discretization, which is required to solve these partial differential equations, which typically means you either create some kind of grid or you create some kind of mesh to actually discretize these equations, is that you get convergence which is not uniform. That means you converge at different points, but there is a slight difference in the level of convergence. Now, this is something which leads to numerical noise. So the complex calculations which take place in various models, when these models are run to perform the simulations, they introduce numerical noise in the objective function and constraints. So you may think theoretically that your function looks like this. You would want your function to look like this. That is a very smooth curve in the design space. But in reality, you are running your simulation at some discrete points, and these points may come across like this here. And your computer program or optimizer may actually settle on some minimum point here and think this is the minimum point. So one of the things which you could do in any such situation is to smooth this out, and the smoothing could be done using a response surface. So this is one more advantage of a response surface. And we have done problems where we have used rough convergence criteria. That is, instead of converging your code to say 10 to the power minus 10, you could converge it to 10 to the power minus 2. And that would save a huge amount of computer time in many numerical simulations. And by using these low converged models and then fitting response surfaces through the solution, you actually are capable of getting as good solutions as if you had done a very deep level of convergence. So these are some of the tricks again one can use in optimization. I have mentioned many times before that this is more an art than a science, and so various tricks are possible. So any kind of non-smooth behavior of the objective function can lead to problems for gradient-based method, and also the presence of spurious local minimum points. And therefore, one of the ways to counter it is to smooth the function out using quadratic response surfaces, for example. So response surface method tends to smooth out these spurious minimum, and in some cases, if you do not do this, your optimizer may think one of these spurious minimum is actually the minimum point, because what may happen is that the gradient may become 0 at this spurious minimum. And as far as the optimizer is concerned, it's going to stop here and feel very good that it's got this minimum. It won't know that this is a spurious minimum. So again, spurious minimums could be smoothed out using response surface methods. So again, this is one more reason for the popularity of response surface method in many multidisciplinary design optimization problems. Like I told before, such problems would involve solving a lot of partial differential equations in the fluid and structural domain, and you would have nonlinearity present also. So you may have situations where different people, different groups, different codes do not converge to the same level, and a lot of these aspects can be mitigated by using response surface methods. So I will end lecture 51 here. I think we are coming to the end of chapter 6 in the book on response surface methods. My next chapter being the last from this chapter, or my next video is the last from this chapter, and we are going to review all the response surface methods there. I will see you in my next video. See you then.